In this video, we're going to show how for small variations in the voltage across the diode equation relating the diode current to that of the voltage can be replaced with a linear equation. Let's say that again. For small variations in V sub D around its bias voltage, we can use a linear model to determine the current resulting from these small variations rather than the exponential model. Now, there are applications where a diode is biased to operate at a certain point in the forward bias region of the diode curve at the DC values of V sub D and I sub D. So we're talking about a point well within the operating region of the diode where that point is defined by some DC voltage V sub D and a corresponding DC current I sub D. And then superimposed on this DC voltage, we're going to have some small variation as a function of time. So the voltage across the diode will be varying away from the DC point, both in adding to it and also subtracting from it. And as we've seen, due to the exponential relationship between voltage and current, small variations in the diode voltage correspond to or cause relatively larger variations in the current. How do we analyze this situation? Well, let's start with the diode equation for a given DC voltage V sub D and the corresponding DC current I sub C. Throughout this derivation, we're going to go pretty slow and methodically. We need to pay close attention to the variable names and the subscripts. In fact, let's just recall the convention that we've chosen. When the variable name is a capital letter and its subscript is capitalized also, so it's capital I subscript capital D, that's going to refer to a DC component. When the variable is a lowercase and the subscript is a lowercase, that will represent an AC component. When the variable is lowercase and the subscript is uppercase, that's going to represent a combination of this AC and the DC components, or we sometimes refer to that as the total current. We're going to go very closely, and as we do so, you'll want to pay close attention to the variable names that we're using, because we're going to be talking about, sometimes we're going to be talking about the DC component, sometimes we're going to be talking about the AC component, and sometimes we're going to be talking about a combination of the two. So starting with the diode equation, where the voltage across the diode is just the DC component. And now let's add in this time varying component so that the total voltage across the diode, lowercase v, uppercase D, now a function of time, will equal the DC component, just our bias voltage, plus this small signal time varying component, lowercase v, lowercase d, and it's a function of time. We'll take now this expression for the voltage across the diode and replace it into here in the diode equation, giving us this expression here. So you can see that we have e to the voltage across the diode now is now the sum of the DC plus the AC components. Using the properties of exponents, when you have e to the something plus something, you can write it as the product of e to the something times e to the other thing. So expanding this on out into two exponential terms, we have this. Notice this is still the total current. It's lowercase I, uppercase D, which means that there's this expression here contains the information of both the DC component and the AC component. Now, notice here, this term, that is just the DC component. This I sub s e to the uppercase V sub uppercase D is just the quiescent current, or the DC current that resulted from the constant DC voltage. So in this expression, we replace this with I sub D, giving us the total current then is equal to I sub D times this exponential term involving only the AC component. Now here's where the magic of this derivation comes from. Recall the Taylor series expansion for the exponential function e to the x. It's equal to 1 plus x squared over 2 factorial and so on. We have e to the V sub d over V sub capital T. So we're going to expand that. E to that exponent can be written in its expanded form, infinite series, as 1 plus this raised to the first power plus this term here squared over 2 factorial plus so on for an infinite number of terms. But underlying all this is that this V sub d term here is going to be relatively small. We're not going to be able to allow for large swings away from the quiescent voltage. This is just the small signal model. But when we restrict ourselves that way, V sub d, which is small, if you square it, that's going to be a whole lot smaller than just a small V sub d. And if you cube it, that's even smaller. Thus, for small variations in V sub d, we can ignore the higher order terms, the x squared, the cubed terms, and so on. And we can replace this exponential expression with a linear expression. Distributing this I sub d, again, that's just the DC current. Distributing it to both of these terms, we get then, and this is the take-home message, the total current resulting from a DC bias voltage with slight variations can be thought of as, or can be written as, equal to the sum of the DC component plus a scaled version of this varying voltage. You'll notice that this scaling term has units of amps per volt. Well, that's just 1 over resistance, or 1 over ohms. And what we see here then is that the total current is equal to the DC component plus this AC varying voltage times 1 over R, or divided by some resistance quantity. In the next video, we'll address what is this resistance quantity.